All right, so let's start with the madcap. Or did we do that one already? Yeah, we did that one already. And we did that one already. Sorry, I don't have a new madcap. I have a riddle. How can you add 8 eighths to get the number 1,000 using only addition? So that'll be something that you can think about and bring me on Monday if you have it. Okay, so 8 eighths using only addition, you got to make 1,000. So just think about it, and you can write it on your paper if you want to. That's up to you. Patterns are all around us. Okay, finding and understanding patterns gives us great power. With patterns, we can learn to predict the future, discover new things, and better understand the world around us. Let me see if I can make it a little bigger. I'm not sure if I can. I'll try. Make it a little easier for you to see it. Okay, so finding and understanding patterns. So you can see that this unit's not going to be the longest unit as far as this one. I guess that was better. And there is a website listed right here, mathisfun.com, patterns. You could actually check these little pattern things out. And there's little matching games, little pattern games that you can check and see if you can figure out the pattern and stuff like that. So there's a match color, there's a match shape, and there's a match numbers. If we have time at the end, we'll come back and look at that. But the website is on your notes, so if you do want to check it out, hopefully I can show you at the end if we have some time. But we mainly use patterns to predict. I mean, that's the main thing. We want to predict what we think is going to happen. And so we use patterns to do that. Inductive reasoning is basically what we call using patterns. So it says, will your car start tomorrow? Well, if it's started every morning since you bought it, you would think that, yeah, it's probably going to start tomorrow. The pattern is that it's been starting every day. So you would think that, yeah, it's probably going to start again tomorrow. So that's called inductive reasoning. So when you reason that what has happened before will happen again, without exception, you're using inductive reasoning. So if you reason what happened before is going to happen again, that's what we call inductive reasoning. We have a couple of vocabulary words. One is conjecture, and a conjecture is an unproven statement or a guess based on observation. So it's like your hypothesis. This is what you think is going to happen. So you make a guess at it. And then you try to prove it right or you try to prove it wrong. Be on the website. So if you do get behind on the notes, they will be on the website. You can get them. So a conjecture is a guess. That's what you think is going to happen. You're looking at a pattern. The pattern's been my car started every day. So my guess is it's going to start again tomorrow. Now, does it have to start tomorrow? No, because you're just using a pattern to make a guess and to make a conjecture about it. Inductive reasoning, like what we just said, is observing data, recognizing patterns, and then making a conjecture. So you look at the data, you look at a pattern, you see if there's a pattern there, and then you make a conjecture. So, I mean, I could get data on everybody's eye color. I could say, well, I got 40 students in here, let's say, or 39 students in here. I'd say 80% of them have brown eyes. So that means at school, 80% of the kids will have brown eyes. That's just a pattern. I'm using a pattern, I'm using data, and I'm saying this is going to be my guess. That's called inductive reasoning. So if you're looking at this pattern right here, this one down here, 1, 2, 3, 5, 8, what's our conjecture? The conjecture is that the next number is going to be 13. You see a pattern? You know what the pattern was in those numbers? How did I get 13? I add the previous two numbers to get the next number, right? So I added 1 and 2 to get 3. I added 2 and 3 to get 5. I added 3 and 5 to get 8. So 5 and 8, the conjecture would be that the next number is 13 in that pattern. That would be your guess. That would be what you think it is. What do you think would be the next number of little dots in that picture? We have 1 dot, then we got 3 dots, then we got 6 dots. I'm thinking 10 dots, like the bowling pins, right? So you're adding, here you're adding 2, then you're adding 3, so you're going to add 4. 6 plus 4, then you're going to add 5, then you're going to add 6. So you're adding the next number each time. That would be our conjecture there, that the next figure is going to have 10 dots. What was that? You can write it down, put your name on it. The first 4 students have brown eyes. So I would reason that all students might have brown eyes. That would be a conjecture. Now, is that correct? No, because probably not all students are going to have brown eyes in here. But if I look at a pattern and say, okay, they have brown eyes, they have brown eyes, they have brown eyes, also everybody has brown eyes. So that could be a conjecture. It's just a guess. Not a true or false statement until you prove it to be true or false. So that would be just a conjecture. All right, moving on. Let's look at deductive reasoning. Deductive reasoning, when I hear deductive reasoning, I kind of think of Sherlock Holmes. You know, just the facts, man. Just give me the facts. That's what deductive reasoning is. Okay, so deductive reasoning is using facts. So one morning your car will not start. What could have caused the problem? You scan the instrument panel and you notice that the headlight switch is in the on position. You look around, the car doesn't start. You look around and you see that the headlight switch is in the on position. Now the headlights aren't on, but the switch is in the on position. So that means that probably the car was bad. The lights were left on all night long. So the battery's dead. So you would deduce that my car didn't start because the battery was dead. So that's what we call deductive reasoning. So linking the headlight switch with the car's failure to start is an example of deductive reasoning. So using the facts that, hey, I see it was on the on position, that's a fact. You got in the car and it was a fact that it was on. The fact is the car doesn't start, so the battery's dead, so that's why the car is not starting. Those are just facts. Using facts to make a conjecture or to make a deduction. So we call that deductive reasoning. To deduce means to reason from facts. You're not looking for patterns with deductive reasoning. You are just give me the facts and then I'll tell you what's wrong. When you reason deductively, you reach a conclusion using logic. I don't know if you have looked at, I know Mariana so far is the only one that actually did that logic puzzle that's on the website. But this is the reasoning you're using with that puzzle, deductive reasoning. There are clues, there are facts. Those facts you have to put in the little chart, and then you make the chart up and you try to get the facts to come out right. When the facts come out right, then you have your answer. So you're using facts to do deductive reasoning. Basically what you're doing is starting with a statement that's true and showing that other statements logically follow from them. So look at the following based on the car example. For a car to start, the battery has to have energy. Is that a fact? For a car to start, your battery has to have energy. Car headlights left on all night will drain the energy from the battery. If you leave your lights on all night long, the battery's energy will get drained. That is a fact. So if this is a fact and this is a fact, when the headlight switch is on, the headlights are also on. That's a fact. So I've taken these three facts, and from these three facts we make a conclusion that the car's not going to start because the battery's dead. So all of these statements will lead us to the fact that the car will not start. So do you see how the chain of facts moved us on to the last part? So this is the one section in geometry that we really don't talk about shapes. We talk about facts. I mean, the reason we do this is because when we do get to certain shapes that we want to prove things, we have to know how to prove something. So we have to be able to take statements that are facts and use those as proofs. That this is a fact, so this shape has to have this, or this shape's got to have this. So we have to learn how to use facts. So that's what we're doing here, is we're learning about, deductive reasoning where we use our facts, or inductive reasoning where we use patterns. Okay, there's three laws of deductive reasoning. So now we would be on page 2 here. Here we go. We didn't get to the bottom. Never mind. There's more on page 1. Sorry. It says all the facts together could be written as one conditional statement. Conditional statement. Those are important in geometry. Those are how we prove stuff. Here's the conditional statement that we could use. If the headlights are on all night, then the car's not going to start. You could take all those facts together and put one conditional statement that if you leave your headlights on all night, then the car will not start. That's called a conditional statement. Conditional statements have two parts. They have a hypothesis. Okay, so I would underline this part right here. That's my hypothesis. And I would underline this part right here, and that's my conclusion. Your hypothesis is the if part. If this happens, that's my hypothesis. If this happens, then this is going to happen. So if it rains outside, then the baseball game will get canceled. So that's your conditional statement. So if you look outside and it's raining, you could then conclude that the baseball game is going to get canceled. Can't say that with soccer or football because they'll still play it in the rain, right? When written in if-then form, the phrase if, the follows if is our hypothesis, and we use letter P. Letter P is what we use for hypothesis. Okay, well, the phrase that follows then is the conclusion, and we use letter Q. So I could actually say here at the bottom, if P, then Q. If this happens, then this happens. P stands for my hypothesis, Q stands for my conclusion. So if 2 points lie on the same line, my hypothesis, if they lie on the same line, then they are collinear, my conclusion. We learned about collinear last week, that points that are on the same line, they're on the line together, co means together, that they're collinear. So if points are on the same line, that's my hypothesis, then they are collinear. If P happens, if they're on the same line, then Q has to happen. They're going to be collinear. So if P, then Q is a common conditional statement thing that we use. So you got to know that the P stands for your hypothesis, the Q stands for your conclusion part. Again, if you miss any part of these, they'll be on the website later tonight. I'll upload it, put it on for you. A couple of examples. Write a conditional statement. So write an if-then statement. If you add equal quantities to each side of an equation, then the equation is still in balance. So we'll just do the first one, and then we'll move on. If you add equal quantities to both sides, or to each side of an equation, That's my if. Okay, the statement just says you can add equal quantities to both sides of an equation and it's still in balance. So if I want to change it to an if-then statement, if you add equal quantities to each side of an equation, comma, then the equation is still balanced. So that's just an if-then. You should be able to do B and C on your own. If you're a police officer, then you're government employees. If an angle is formed by two rays, then it has a common endpoint. So those are kind of things that you could write in later. I'm just going to do the first one there for you so we can get to the last page. I just want to finish 2-3 here. So we're going to get to last page. It says 3 laws of deductive reasoning that to make a valid argument. Okay, now you don't really have to memorize these, but you need to know that they make sense. Okay, the law of detachment says if P to Q is a true statement and P comes true, then Q will come true. So watch this. If you mispractice, then you will not play in the game. Okay, if that's a true statement. If your coach says that and he means it, and let's say you mispractice, on Tuesday you mispractice, then what has to happen? You have to miss the game. If that's a true statement, you will conclude that you're not going to play in the game. If P to Q is true, then if P happens, Q must happen. Now, it's just a real-life example of what could be a conditional statement like that. So just know that this is called law of detachment. That if you know if that's a true statement and P happens, then Q is going to happen. That's called law of detachment. So, I mean, you could think, I was using the baseball example. If it rains, the baseball game will get canceled. If that's a true statement and you see it raining outside, then what has to happen? The game's got to get canceled. Okay, we call that law of detachment. That as long as you know that this is a true statement and the first part comes true, then the second part has to come true. Okay, that's called law of detachment. The last one is called law of syllogism. I know it sounds kind of weird, but it's called law of syllogism. If P to Q and Q to R, now there's a second statement now, are true statements, then P has to be able to go to R. Then P to R has to be true. Now here's a real life example that will help you. Okay, so just write that down really quick and then we'll follow this example. Okay, what conclusion can we make from the following? If a bird is the fastest on land, that's going to be my P statement. So I'm going to put a P above this. If the bird is the fastest on land, then my conclusion is my Q statement. Okay, that's not really a good Q. So this will be Q right here. So if P happens, or if it's P, then Q. So there's my P to Q statement over here. If it's the fastest on land, then it's going to be the largest of all birds. Okay, if a bird is the largest of all birds, that was my Q statement. So I'm going to put a Q right here. Because the largest of all birds was Q. Then it's an ostrich. That's my R statement. So notice how the Q is in common in both of them. So if it's the fastest, then it's the largest. If it's the largest, then it's an ostrich. So what can we basically say down here? If it's the fastest, then it has to be what? An ostrich. You can go directly from P to R. So that would be your conclusion. If the bird is the fastest, then it has to be an ostrich. So that would be the law of syllogism. That's just 2.3's notes. Okay, we'll do 2.4 Monday.